right, well, we have a test coming up tomorrow. Overall, really good job on those quizzes. Some little things, right, that we need to make sure we shore up before tomorrow. But overall, good. We will do a little bit more review on the math, and I think we've got another ramp problem. So we'll work on that. That was the one thing that gave you guys a little trouble still. But we'll be reviewing that here in just a little bit. Go and jot down some review notes real quick. It covers chapters 10 and 11, as I've been announcing for the past a couple of days. Remember, chapter 10 was uniform circular motion, periodic motion, specifically springs and pendulums. So chapter 10 was uniform circular motion, periodic motion with springs and pendulums. Penduli? Anyway, I had an interesting one in the car this morning. You know, if you take the plural of box, boxes, but plural of ox is oxen. You know, so it doesn't match. You know, box, ox, oxen, box, boxen, two boxen, 20, 50 boxen of candy. Anyway, springs and pendulums, I believe is the correct plural. And then chapter 11 was work, power, and machines. Work, power, and machines. So we're doing kind of an overview of what the content will be on the test. So what is uniform circular motion? See what we remember. It's been like a month because of Thanksgiving break. It's been like a month since we talked about uniform circular motion. What is that?
Motion on the same speed, on the same line around a circle.
Okay, motion around a circle or in a circular path at a constant speed. Same speed, circular path, or same speed in a circle. Is the velocity constant? The speed is, the velocity is not. Why not, Audrey?
It changes direction.
Constantly changing direction. Anytime there's a change in velocity, now we usually think change in speed, but anytime there's a change in velocity, we call that class acceleration. So therefore, an object in uniform circular motion, remember we said it's constantly accelerating in which direction? Towards the center of that circle, right? Because if it were anything else, it would impact the speed, but it's perpendicular to the speed component, so it is perpendicular toward the center of the circle. What do we call this center-seeking acceleration? Acceleration. Good. Centripetal acceleration. Good. And quick reminder, go and jot the equation down there. A sub c equals v squared over r. So there was the first equation that you need to know for the test. A sub c equals v squared over r. And we said you won't have acceleration unless there is some force that causes it, right? So what do we call a force that causes centripetal acceleration?
Centripetal force.
Centripetal force, very good. And so for centripetal force, since force is mass times acceleration, it'll be mv squared over r. And there's the second equation for this test. So I said, well, what are some of the actual forces that can be centripetal forces? Forces that will cause uniform circular motion. Gravity, in the case of the moon going around the Earth, for instance, there's a gravitational pull that keeps it going in that circular or roughly circular path.
Tension.
Tension, if you swing something around on your finger from a string, the string pulls inward, there's that centripetal force.
X.
Okay, if an object is going around a, you've seen those things, right, where, okay, backtrack here. Maybe I'm dating myself here. Do you know what a gumball machine is?
Yes.
Okay. Now, do you know what the cool gumball machines look like, right? Where it drops the gumball and it spins around and around?
Yes.
Okay. So, actually, it wasn't that. It was something else. I think it was it was like a Salvation Army coin collection thing, but you drop the coin in and it rolls around and around. Okay, you've seen that. Okay, the reason it's going in the circle is there's a component of the weight that pulls it inward. It's got its own inertia, of course, caused by the dropping action, right? It develops a velocity, but then it goes in that circular path because of its weight in the X that pulls it inward. So yeah, good example. Man, I haven't seen one of those in a long time. That was cool though. I was like, I'd gladly give another penny. You know, they want quarters and stuff, or shove some dollar bills in there. But yeah, that was cool.
There's one at Dairy Queen.
Dairy Queen has one. On which one?
Macon Road.
Macon Road Dairy Queen has one of those. Gotta stop by Macon Road Dairy Queen now. and not for what is it that Dairy Queen's famous with? Blizzard, right? Blizzards, yeah. I was like, Frosty, no, that's Wendy's. Anyway, neither of them endorse this channel, though, so I don't care. Anyway, there's another force that I'm thinking of. Maybe as you're driving, as you make a turn. Friction force, right? Friction force can also be, even if you're just walking in a circular path, would be friction force. So all those different forces are centripetal forces. What do we call the reaction force? The center fleeing force that goes outward.
Centrifugal.
Centrifugal?
Yes.
It doesn't spend much money? Close.
Centrifugal.
Centrifugal force.
Yeah.
Centrifugal force. Fugal. That was good. All right. From there, we talked about motion. It repeats itself over and over after the same lapse of time. Periodic motion. We then said, more specifically, if the motion repeats itself after the same lapse of time over the same path, we have what's called oscillatory or vibratory motion. But oscillatory, with the silent C, is the term that we use in this class. And then we said, if the oscillatory motion, that is periodic motion, that is motion over the same lapse of time, over the same path, happens to be caused by a restorative force that's proportional to displacement, we call this simple harmonic motion. Good. And we looked at two types of simple harmonic motion. First of all, we looked at the spring, remember, where we hung the spring here vertically, and we put a mass on it. We allowed the mass to stretch the spring until it hung motionless, or as close to motionless as I could get it. At that point, there were only two forces acting on the mass. You're right about the gravity, but we didn't call it tension force. That would be a straight string, would be tension. Restorative force that was in the spring. And we said that when the restorative force upward and the weight downward were in balance with each other, we were at a point called equilibrium. If I then either pushed the mass upward or pulled the mass downward away from equilibrium and released, it would begin to oscillate. What do we call that displacement from equilibrium? And for the most part, however far down I pulled it is how far up it would go, or however far up I pushed it, or down it would go. That distance from equilibrium, I mean, eventually it leveled off, but initially it would keep that same displacement over and over again. Called an amplitude. The amplitude of oscillation, that displacement from equilibrium. Now, we also looked at when we just had the spring hanging here, and then we put the mass on it, the spring would stretch out a certain amount. That's not displacement, right? That's just an amount of stretch. What letter did we use to represent the stretch of the spring? X. And we said that the amount of stretch would be equal to the weight that was pulling on it, or the force that was pulling on it, over the K. And the K here is the spring constant, right? And therefore we could say that K equaled mg over x. So we could take the weight of the object divided by the amount of stretch, and that would give us the spring constant. Now, of course, go backtracking real quick on some units. Of course, acceleration we know is always meters per second squared. Force is measured in newtons, but the spring constant was a little bit different because we don't use that very often. So remember, the spring constant, either newtons per meter, because you can have newtons from the force and meters from the stretch, or if you worked this out with meters, it would cancel with the meters per second squared in gravity and give us kilograms per second squared. So either one of those units could be used for the spring constant. So a little refresher there, since it's been so long since we've done any math with this. We said that as we pulled the mass down and let it go, it would go up and down and up and down and up and down and up and down. And the time it took to go up and down once was called the period. Period is the time for one oscillation. However, if it were to go up and down really fast, like that, really fast up and downs, then we could count how many up and downs or how many oscillations took place per second. What term refers to oscillations per second or per unit time? Frequency. What's the relationship between frequency and period?
Period is unit time and frequency
is per time, so they're reciprocals. Remember, frequency is the reciprocal of period, and therefore period is the reciprocal of frequency. Of course, period is just measured in seconds because it's time. What about frequency?
Per second. Hertz.
It is per second. We call it hertz. Hertz is usually what we'll use for the frequency. Now remember, we said that when you pull on the mass and it goes up and down, up and down, up and down, if you pull on it a little bit with a small amplitude, it goes up and down and up and down and up and down. And if you were to pull a lot more, it would go up and down and up and down and up and down. But it would still take the same amount of time. Remember, we said the amplitude really didn't matter because it would accelerate more greatly with a greater amplitude, right? But it would still take the same amount of time because although it's covering more distance, it's moving more quickly on average. So we said amplitude doesn't affect period. What two things did affect the oscillation of the spring?
The weight
The mass that we suspended from it,
and
the strength of the spring itself, right? Or we would say the spring constant, right? So those two things. So remember, we said that the period of a spring can be found, and this was the next equation, 2 pi times the square root of m over k. 2 pi times the square root of m over k. And of course, we'll look at some math with that here in a little bit. Let's see, right there. Perfect. All right. There you go, Kendall. Looking out for you. Went to all of that. From there, we talked about the pendulum. And we talked about the simple pendulum. But the key to something being a simple pendulum is that the connector is massless. So we said, really, truly, there is no such thing as a simple pendulum. But we said the pendulums that we made in class, for the most part, were pretty much simple penduli because the masses we were hanging, there was such a vast difference between that mass and the mass of the string itself that was used as the connector. It might as well be a simple pendulum. So pretty much the things that we talked about worked. And we said for a simple pendulum, you pull it back, and it goes back and forth and back and forth and back and forth. And of course, you could pull it back to your nose, not quite touching your nose and let it go to swing out. It's come right back at your nose, but it wouldn't hit your nose, did it? Didn't hit nose anytime. Unless you moved your nose forward and then it hit nose. But anyway, back and forth, right? And the time it takes to go back and forth once is called the period. The number of back and forths per second, if it could do that really fast, which none of them did, would be called frequency. Of course, in our case, the frequency was always fractional hertz, right? Because it was fractions of an oscillation per second, because it took usually more than a second to oscillate. We said, what was it that affected the swing of the pendulum, the period of the pendulum? The mass didn't, remember. Now, when the mass affected the length by that little bit, we said that did. But, I mean, if the length had been able to stay constant, the mass actually didn't affect it. The length of the connector was the single biggest thing that we could observe. Now, there's another factor we are not able to observe in here. What is it that causes the pendulum motion in the first place? I pull it back, and if I were to let go, it doesn't stay there. Why not? Yes, you're not wrong. Gravity. Gravity pulls on it. Now, it's not able to pull straight down because of the string, so as it tries to pull straight down, it ends up pulling it forward because there's some tension forward as well. But the gravity, and a stronger gravity would pull more rapidly, which would cause it to affect the period, right? So although we couldn't observe it because in this lab, gravity is what it is, we said that those are the two things that affect the period of the pendulum. The length of the connector, specifically the square root of the length of the connector, and inversely proportional to the square root of acceleration due to gravity. We said the mass does not affect the period, and there was another thing that you might think would affect the period, but it doesn't. Kind of like with the string. How far back you pull it, right? We call that the amplitude. Just in your notes, write down laws of the pendulum. Laws of the pendulum. In either page 153 or find it back in your notes. So these are on page 153 if you want to study from your book. If you want to go back and study from your notes, just find where the laws of the pendulum are. These laws of the pendulum then led us to our equation for the period of the pendulum. Very similar in setup to the spring. T equals 2 pi times the square root of, but the mass doesn't affect it like it does the spring, but the length And the spring constant isn't what drives this motion, but gravity is what drives the motion. So T equals 2 pi times the square root of L over G. And that wraps up what we need to know for chapter 10. All right? It's been a little while since we've done anything with chapter 10. Questions on chapter 10? All right. Moving into chapter 11, we talked about work, and we said work is a transfer of energy from one body to another as evidenced by motion. Something's got to move for energy to be transferred. Like, I will transfer my energy into this bottle. Nothing's happened. No energy. Actually, it did kind of move. Now, to be fair, if I grab the bottle like this, you ever notice when you hold a water bottle, it feels nice and cool, and over time you don't really notice it feeling cool anymore? There is energy flowing. It's called thermal energy. We'll get to that in chapter 14. But as far as like normally what we think of as energy, just touching the bottle doesn't transfer any energy. It's if I cause the bottle to start to move. Even if I did this, there's transferring energy into the bottle. But it has to be motion. We said work is measured in what units? Joules, or in the U.S., foot-pounds. And this is because work is dependent on or proportional to two different things. What is work proportional to? Displacement and force. The amount of force that's applied to the object and how far does the object go. So our next equation, first equation from chapter 11, is that work equals force times displacement. And remember, work is measured in either joules or foot-pounds. Joules or foot-pounds. Remember we said that when we look at the force, it's not actually how much force is exerted, but how much of the force that was exerted happens to be in the same direction as the motion or the displacement, right? So remember, when force is applied at an angle, for instance, if I drag this desk, okay, my force was actually exerted at an angle, but the upward force didn't do anything, right? It didn't move the object. I suppose you could say lightened the friction, but I mean, it's on rollers. There's minimal friction anyway, right? So the lifting aspect didn't do anything, but the component that pulled toward me, that's what did the work. And so, okay, right there in Kendall's suite, right there. Okay, that component is what is the force used there. We talked about negative work when you set something down because your force is in the opposite direction. We looked at no work being done when you're holding something, but you're not moving it vertically anymore. The time rate of doing work we call power. Power is how much work you accomplish per unit time, which gives us the next equation, P equals W over T, work per unit time. I said that my son and I could probably both do the same amount of work in some instances, right? Where not too much force is required, but I'm able to do the work more quickly, right? That means there's more power even if the work is the same. Remember what we use for power? Watts. I love my wife Watson. Watson's powerful love. All right, so the W here is watts, not work. Okay, this W is work, and this W is watts, the unit. Or we could use in the U.S. foot-pounds per second. And then there was another rather ambiguous unit that Isaac Watt was the hymn writer. James Watt came up with called horsepower. And you need to remember that 1 horsepower is approximately equal to how many watts? 746 watts. And he actually defined it as being equal to how many foot-pounds per second? 550 foot-pounds per second. So that's power. From there, it was all about machines. And we reviewed machines in our last lesson. We took a quiz over machines, know what the machines are, know the terminology, know the AMA and the IMA for these different machines. But for sake of time, I'm not going to go over all of that again. Obviously, if you want a little more review, go back and watch yesterday's lesson, the part before the quiz, because that was very in-depth there. Well, okay, I'll at least hit some of the key terms. Just anyway. Long and flexible object that pivots. Lever. Ramp.
Inclined plane.
2 inclined planes back to back.
Wedge.
Inclined plane wrapped around a rod.
Screw.
Circular lever used to redirect force. Multiple pulleys used in combination. Block and tackle. Two wheels that are connected.
Wheel and axle.
Wheel and axle. And the ratio of output work to input work expressed as a percent. Efficiency. Output force to input force as a ratio. AMA, input distance to output distance, IMA. All right, let's see if the projector shut down. I mean, it might have already shut off. No, it did not. That's happy. Okay. Good, because it takes forever to warm up. Let's take a look at some math problems here now. And at your seats. Go ahead and get a head start on this, and then we'll work it together. That is a really big string. That's probably hitting walls. Or maybe he's outside. Let's hope he's outside. Obviously, it's the air resistance that's actually going to keep the plane in the air while he spins it around and around, but you know, whatever, we're ignoring that. If it's going around in a circle and it's going around at a constant speed, what do we have going on here, class? Centripetal force. So when it says determine the tension, that is the centripetal force. So it doesn't actually come right out and say find the centripetal force, but that's what's being implied. Does that make sense? So to find centripetal force, what's that equation, class?
F sub c equals mv squared over r.
mv squared over r. So I need to plug in the mass, I need to take the speed and square it and divide it all by the radius. What is the radius?
1.5 meters.
Well, the string is 3 meters, right? So here's the little boy, and there's a 3-meter long string, and there's the airplane. Okay? And it's going around him in a circle. So what's the radius?
3.
The actual 3 is the real radius here. What about the speed?
3.7.
The 3.7 meters per second. And then what about the mass?
That's weight.
Yeah, it gives us weight, doesn't it? So since the weight is 28 newtons, what do I have to do to find the mass, class? I'm going to have to divide out the 9.8 meters per second squared. So what is the mass?
2.85.
Yeah, 2.857 blah, blah, blah kilograms. I'm just going to keep it on the calculator, the 2.8 blah, blah, blah. And we'll multiply that by the 3.7 squared. We'll divide all of that by 3. And how much force, how much tension is in this rope, or, I don't know, it says string first and then it says rope. I don't know who writes these. What is the tension or the centripetal force here, class?
13.0.
And it's 2 sig figs, right?
Yeah.
So we get
13.
13 force measured in newtons. Or remember, work is in joules, but force is in newtons. All right, and questions on this? Questions on this? All right, another one for you here, and that's unfortunate. The let me see what that actually says. It blocks out the kilogram of the mass.
I think so.
Oh, it doesn't even matter. It's the 4.5 kilogram mass anyway. So yeah, you don't necessarily need this number. I just realized this little box is blocking it, but you could just take this off and just say find the period of oscillation of the mass. So we're good. Oh my. Friction. So I slide this over to help you out a little bit, to help Kendall out. And I realized I put it right in your line of sight. My bad. There. Rough life, rough life. Remember, we represent the stretch with the letter X. So when I go to find the spring constant, what is that equation for spring constant again, Michael?
Okay.
Right, so I'm going to take the mass, which is 6 kilograms, times G, which we assume to be 9.80, and the stretch, but I've got to change it from meters to centimeters, class. And so this is going to be quite the, it's going to be quite a strong spring. Again, 6 kilograms. I mean, you remember the big weight that I showed you of my big masses? 6 of those, and only stretches like that far. So this is an incredibly heavy-duty spring. Perhaps slightly dangerous, I'm not sure. Yeah. What is the spring constant here? 784 kilograms per second squared, or you could say 784 newtons per meter. Though, how many sig figs? 2. So for part 1, I'm going to round my answer to 780 newtons per meter, but I know the actual number is 784, and that's what we'll have to use as we move forward. Did we get the first part of the problem correct? All right. Second part of the problem says we now take that 6 kilogram mass off and we put a 4.5 kilogram mass instead, set it into motion. We want the period of oscillation. All right, for that equation, we're going to use what, Audrey?
2 pi times the square root of m over k.
So it's 2 pi times the square root of, now again, the mass is no longer the 6 kilogram mass, it's now a 4.5 kilogram mass. But we're still going to use the 784 spring constant. It's a very strong spring, so we assume it's going to oscillate very rapidly. And it does. What is the period of oscillation? Class?
0.476.
Yeah, 0.476, blah, blah, blah. Or if we round off to sig figs, 0.48 seconds. If it had asked for the frequency, what would I do? Take the reciprocal. So if it asked for the frequency, we get 2.1 hertz when you take the reciprocal to 0.476, blah, blah, blah. It didn't ask for that, I just thought I'd point that out. Questions on spring. Are we going to be good on spring problem math tomorrow? Feel good about that one? All right. Any day now. Did I go too far? No, I was right the first time. Okay. And that's covering up the part of the word determine, but I think you can read that just fine. All right, next problem. Add your seats. I feel like we've done this one before. Oh, well, do it again. Good review. It's unlikely you actually remember the answers. Michael's like digging through his notes. I'll find it. Oh, look at Argo. He's laying at the bottom. I've never seen him do that before.
Oh, wow.
I don't think he's dead though, because if he were dead, he'd be floating at the top belly up, right? That's how fish float when they die.
Yeah.
So surely he's fine. Never seen him like this. Should I show Kendall?
Yes.
I show Kendall the fishy.
Is he older than 18 months?
Well, she can see the fishy even if she's not over 18. It's not going to get Audrey in the camera shot. We don't want Kendall to have to see Audrey. Yeah, I don't know if you can see that or not, but Argo's just sitting on the bottom of the tank, Kendall. Yeah, poor Argo. He looks sad. Looks depressed. Anyway, that's random and has nothing to do with your test tomorrow. Also, Kendall, we have 2 more people who are wanting to be able to see you, so they're missing you too, by the way. So I know you haven't gotten a chance to see them in a while. Having too much fun. I should probably stay focused. But I don't have a test tomorrow, so I'm relaxed. Log. Ground. What's the weight of the log? 140 pounds. It doesn't say that he pulls the log at an angle, though probably he does, but it doesn't say that. So we'll assume the normal force is also 140 pounds, even though it's probably unlikely, which means the friction force is 114.8 pounds, which means if he pulls the log across the ground at a constant speed, which means if he pulls the log along the ground at a constant speed, his applied force must be. All right, so that's the applied force. That's what goes into the equation for work. So when we go to find work, we said work is equal to? Force times displacement is the 114.8 pounds he applied, and he moved the log 14 feet. So we'll multiply that, and we end up with
1,607.2.
And round it off.
1,600.
And our unit? Normally joules, but not on this one. Foot pounds, because somebody decided to give you non-scientific units. All right, questions on the first part. Second part says he does all of that in 3.5 seconds to determine his power. How do we find power? Work divided by time. Well, I have the work on the calculator, just divide that by the time, and I get?
459.2.
And that's foot pounds per second. But it said determine his power in horsepower. Again, how many foot-pounds per second does it take to make a horsepower?
550.
So we need to divide by 550 to get
0.8349.
round it off to the 2 sig figs, we'll say 0.83 horsepower. And there's our 2 answers. Questions on this problem, or these 2 problems, I guess, technically? girls on a seesaw, 6 meters long. One girl's 325 newtons. She sits at one end. The other girl's 370 newtons. How far from the pivot point must she sit in order for the seesaw to balance? Realistically, there's actually probably enough friction that it would balance pretty well anyway, but we're assuming frictionless. And what equation do we need here, Michael? There we go, the law of levers. And if it's a 6 meter long seesaw, then normally the lever arms would both be class 3 feet, or 3 meters, excuse me. But for the second girl, it's not 3 meters, right? Because she's going to have to scoot forward a little bit. The first girl, who's actually sitting at the end, is 325 newtons. And the second girl, slightly larger, 370 newtons. So let's see, Kendall and Audrey. And so yeah, just multiply, divide. And what do we get for the lever arm, or the distance from the pivot point for the second girl? Us?
2.6.
And round it off. 2.635. So when we round off to 3 sig, yeah, it is 3 sig figs, we get 2.64 meters. So again, she doesn't have to slide that far forward, just what, about a third of a meter forward, 0.36 meters forward. So not far at all, a little more than a foot forward. All right, questions on this one? One last one. I told you we will have another ramp problem since that's been giving us a little trouble. And so let's go ahead and take a look at this one now. A 4.5 foot long ramp to get onto the sidewalk, or from the sidewalk. And the building sits 9 inches, 0.75 feet higher than the sidewalk. So you know, like our daycare building, for instance, there's like that little step up. That's what we've got here, but we're using a ramp to get up instead of a step. What do we have to know about every ramp that is not given in the problem? We must know the angle. Again, we're going to have to find the angle. We've looked at a few like this. We have to find the angle from the picture. What trig function allows me to find the angle? The sine, or specifically the arc sine, right? Because we know that the sine of any angle is the opposite over the hypotenuse, but we're going to take the arc sine of that to find the angle. Once you get it, I would put it in the memory of your calculator. And what is our angle, class?
9.5.
9.59. Let me double check that. And 9.59 blah 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 degrees. Alright, questions on the angle, because that's, if you miss the angle, everything's going to be off. We got to get the angle correct. Are we good on the angle? Alright, then you can do the free body diagram from there. All right, did you get in the X exactly 400 newtons? Did you get in the Y 2366.4 newtons into the ramp? And therefore, normal force also 2366.4 newtons upward. Did you get for friction 283.97 newtons? Normal force times that coefficient. So it says the coefficient right here is the 0.12. We're going to multiply that by the normal force, 2366.4. That's where the 283.97 comes from. Now we're ready to actually solve all these different things. Number one says find the force the man must exert. Find his applied force. How do I find applied force?
The weight in X plus friction.
Weight in the X plus the friction. So that's going to come to
683.97.
good. I'm going to go and add the 400. I'm going to store this in memory too, but we're going to round it off to 2 sig figs and say 680 newtons of applied force. But I'm going to use the actual 683.97 for the next thing, which is the AMA. How do I find the AMA for a ramp? Remember, it's output over input, so
22400 over that.
weight over applied force. So the weight is 2400 divided by the applied force, which I just put in memory too. What's the AMA?
3.50.
Now it's 3.508 blah, blah, blah. I'm going to store that in memory 3. But I'm going to write 3.5. Third, they want the IMA. How do I find IMA?
Length over change in height.
Good, length over change in height. So 4.5 over 0.75, or you take the sine of theta and take the reciprocal. It's probably easier to do 4.5 divided by 0.75. What's the IMA?
6.
Exactly 6, but I need 2 sig figs, so I'm going to say 6.0. Finally, we need the efficiency. How do I find efficiency? Good. Output work over input work as a percent, or AMA over IMA as a percent. So I'm going to take recall 3, memory 3, which is 3.508, divide that by 6 to get what efficiency?
0.584.
0.584, blah, 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 but making it a percent, move it 2 places to get
58%.
58.4%, or since it's 2 sig figs, 58%. All right, no homework other than be ready for the test, study diligently, and tomorrow we'll take that test over chapters 10 and 11. Have a wonderful rest of your day, and you are dismissed.